Welcome back to AI.Code.Cast. Today, we're going to be taking a deep dive into a problem that might seem pretty simple at first glance,
Yeah.
but it's got some really interesting kind of depths to it. And it's all about figuring out the maximum nesting depth of parentheses in a string.
It's a classic problem, and you're right.
Yeah.
It's definitely more than just like counting parentheses.
Right.
We're talking about understanding the structure they create.
Uh-huh.
It's like those Russian nesting dolls.
Yeah. Okay, so let's set the scene here.
Okay.
Imagine we have a string, and maybe it's something like this: 1 plus 2, 3 plus 8, 4 plus 1.
Okay.
And our mission, if we choose to accept it, is to figure out how deeply those parentheses are nested.
Okay.
So, like, my first instinct would be to just kind of, like, check every possible combination of parentheses.
Uh-huh.
Is that a reasonable place to start?
It is. That's what we call the brute force approach.
Okay.
It might not be the most elegant way to do it,
Right.
but I think it helps us just wrap our heads around the logic. You're essentially going through the string and looking at every single substring.
Okay, so we're talking about examining each little chunk of the string, right?
Yeah. Every single one.
How would we actually, like, measure the nesting depth within each substring?
You would use a counter.
Okay.
So you would start it at 0. And then as you move through that substring, you would increment it for each opening parenthesis and decrement for each closing parenthesis.
Okay.
And then the highest value that counter hits, that's going to be the nesting depth for that substring.
I got it. Okay.
Yeah.
So in the substring, like 8, 4,
Yeah.
our counter would go up to 2, then back down to 1, and then finally back to 0.
Right.
2 would be the max depth for that chunk.
Exactly.
But doing this for every single substring, that sounds like computationally, it could get really expensive, especially with longer strings.
You are hitting on a key point here.
Okay.
This brute force method has a time complexity of big O of n squared, meaning that, the time it takes grows much faster as the string gets longer.
Right.
Which is not ideal when efficiency matters.
Right. It's not ideal when efficiency matters.
Yeah, not at all.
Okay. So brute force helps us understand the basics.
Yeah.
But it sounds like we need a smarter approach.
Yes.
Are there any hints out there for our listeners who found
a
more efficient solution?
Yeah. Think about how we could keep track of the opening parentheses we've encountered and whether they've been properly closed.
Okay.
So what data structure comes to mind that might help us kind of manage this like open and close behavior?
Open and close, like a door. Or, I think I see where you're going with this.
Okay.
Could a stack be the answer?
Okay, tell me more about that.
Like a stack of plates, you can only add or remove from the top.
Exactly. Imagine each opening parenthesis is like a plate that we're adding onto the stack.
Okay.
And when we encounter a closing parenthesis, we remove the top plate from the stack.
Gotcha.
And so the maximum height of our stack represents the maximum nesting depth.
That's pretty clever. I don't think I would have thought of using a stack for this.
It's a good one.
So as we go through our example string, the 1 plus 2, 3 plus 8, 4 plus 1, we'd be adding and removing parentheses from the stack, and then the highest point the stack reaches would tell us our max nesting depth.
Precisely.
That's really cool.
Yeah, and the beauty of this approach is that it brings our time complexity down to ON, which means it scales much more efficiently as the string grows.
So stacks seem to be a winner in terms of efficiency.
It seems so.
But is there a scenario where a stack might not be the ideal solution? Are there any hidden gotchas we should watch out for?
That's a great question, and I think we should dive into that next time.
Awesome. Can't wait.
Yeah. Stacks are pretty powerful.
Yeah.
But, they do have limitations. Remember, they're really designed for situations where the order of items matters. In this case, we're really relying on that order to make sure that each closing parenthesis matches its corresponding opening one.
Right. It's like making sure each open action has a matching close action.
Exactly.
And the stack helps us keep track of that sequence.
For sure.
But what if things get a little more complicated?
Yeah.
What if we have a string with not just parentheses, but also like square brackets and curly braces?
That's where things get really interesting.
Yeah.
And you're right to question whether the stack approach can handle that.
Yeah, my gut feeling is that stacks could still work.
Okay.
But we might need some, tweaks to our logic.
You're on the right track. The core idea of using a stack, that remains the same.
Okay.
But we need to add a step to make sure we're matching the right types of brackets.
So instead of just checking if the top of the stack is any opening bracket, we need to be more specific about matching parentheses with parentheses, square brackets with square brackets, and so on.
Exactly. When we encounter a closing bracket, we peek at the top of the stack.
Okay.
If it's a matching opening bracket of the same type, then we pop it off.
Got it.
But if it's not a match, say we have a closing square bracket trying to cancel out an opening parenthesis, then we know there's an issue.
That's a crucial addition.
It is.
It's like we're adding a layer of type checking to our stack.
Yes.
Making sure we're not mixing our brackets.
Yeah, absolutely.
Could you walk me through an example to see how this would work in practice?
Absolutely. Let's say we have the string.
Okay.
Can you guess if it's valid or not just by looking at it?
Let me see. It seems like it should be valid.
Okay.
All the brackets appear to have matching counterparts.
All right.
Let's see how the stack handles it.
All right. So we're going to start with an empty stack.
Okay.
The first character is an opening curly brace. So we push that onto the stack.
Got it, stack.
Next comes an opening square bracket.
Okay.
We'll push that onto the stack as well.
Okay, seeing the pattern here. Each opening bracket gets added.
Right.
So stack.
Now we have an opening parenthesis, which we push onto the stack.
Okay, stack.
And then comes our first closing parenthesis.
Right.
So here's where that matching comes in.
Okay.
We peek at the top of the stack.
Yeah.
And we see an opening parenthesis. They're a matching pair, so we pop it off the stack.
Well, the stack shrinks a bit, stack.
Exactly.
Okay.
We continue through the string. We encounter a closing square bracket. We peek at the stack. We see a matching opening square bracket.
Right.
And pop it off.
Stack?
Then another closing parenthesis appears.
Yeah.
We peek again, and this time we see the opening curly brace at the top.
Right.
Not a match. This signals an invalid string.
Ah, that's where the type checking comes into play.
Yes.
Even though the string looked balanced at first glance, our stack-based approach caught that subtle error.
Yep.
Pretty neat.
It is. And the time complexity for this enhanced stack approach remains O(n).
Right.
Even with multiple bracket types, it scales efficiently with the length of the string.
Okay, so stacks are still our heroes here.
I think so.
They can handle multiple bracket types.
Yeah.
And they even help us catch those errors.
They do.
What about space complexity, though? Does adding different bracket types significantly increase the memory we need?
So in the worst case scenario, where the string is entirely made up of opening brackets, the space complexity would still be O.
Okay.
But in most practical cases, the stack won't grow that large.
So stacks are efficient in terms of both time and space.
It seems so.
What about our other approaches? Would brute force or the counter method be worth considering in this scenario with multiple bracket types?
Let's think about it. So the counter method really relies on that one-to-one correspondence between opening and closing brackets. Right.
Once we introduce different types,
yeah,
it kind of falls apart because it doesn't have a way to keep track of which type of bracket is being opened or closed.
So the counter method's out of the picture for this one.
Yeah, I think so.
What about brute force? Could we adapt it to work with multiple bracket types?
We could.
Okay.
But it would become even more computationally expensive.
Yeah.
You would have to check every single substring for every possible combination of bracket types.
Right.
The time complexity would increase dramatically.
So it sounds like brute force is definitely not the right tool for the job in this case.
I agree.
Stacks win again.
Ooh.
They're efficient, they can handle multiple bracket types, and they even help us catch errors.
All good things.
But is there anything that can beat a stack for this kind of problem? Could there be an even more elegant solution out there? That's a great question. It leads us to an interesting thought. What if we could find a way to solve this problem without needing any extra storage space at all?
Wait, you're telling me we could potentially solve this?
Yeah.
Without using any data structures like a stack?
Potentially, yes.
How is that even possible?
There might be a clever way to do it.
Okay.
Think about the core logic of how we've been approaching this problem. We've been really focusing on matching opening and closing brackets.
Right.
But what if we could find a way to track the nesting depth using only a single variable?
A single variable?
Yeah.
That sounds almost too good to be true.
It might be.
Are you hinting at some kind of magical counter method that can handle multiple bracket types?
It's not magic.
Okay.
But it is clever. Let's explore this further in the final part of our deep dive.
Okay, so we're back for the grand finale of our maximum nesting depth deep dive.
I'm excited.
We've explored brute force, tackled stacks.
You did.
Even kind of flirted with that clever counter solution. But you've hinted at this solution using just a single variable.
Yes.
No stacks.
Yeah.
No complex logic.
No.
I'm dying to know how that's even possible.
It really is all about kind of reframing the problem.
Okay.
Instead of focusing on matching specific brackets, we can think about the nesting depth as kind of like an altitude.
Okay.
And so we'll just use this one variable to track our current altitude as we go through the string.
Okay, I'm visualizing like a little climber moving up and down as we encounter different brackets.
Yes.
How would this altitude tracker actually work?
So let's imagine that we're starting at an altitude of 0.
Okay.
Every time we encounter an opening bracket, whether it's a parenthesis, square bracket, curly brace, whatever, we increase our altitude by 1.
So each opening bracket is like taking a step upwards.
Yes.
On like a mountain path or something.
Exactly.
What happens when we hit a closing bracket?
When you encounter a closing bracket, you decrease your altitude by 1.
Okay.
Regardless of the type.
Gotcha.
The key here is we're not really concerned about matching specific types anymore. We're just simply tracking that overall nesting depth.
That's brilliant. So it's like our climber is descending back down the mountain.
Yes.
But what about those mismatched brackets we talked about earlier? How does this altitude approach handle the invalid strings?
So that's the beauty of it. It actually handles them very gracefully.
Okay.
So if we encounter a closing bracket when our altitude is already at 0, that means there's no corresponding opening bracket, right?
Right.
But instead of throwing an error or anything, we simply ignore it.
So our climber just shrugs and keeps going.
Exactly.
Even if there's no step to step down to.
Yeah, the altitude can never go below 0. And the highest altitude our climber reaches throughout that whole journey, that represents the maximum nesting depth.
I love it.
Whether the string is valid or not.
This is amazing. It's so simple yet so powerful.
I know.
It's like we've found a way to measure the depth of a valley without worrying about whether each cliff has a perfectly matching counterpart.
That's a great analogy.
And this approach, even though it feels deceptively simple,
I know, right?
achieves the same time complexity as the stack.
Yeah.
But with the added benefit of using only O1 space.
Amazing.
Meaning constant memory usage.
I love it.
This just blows my mind. We've gone from this brute force approach that just felt clunky to this elegant solution using just one variable.
It's pretty cool.
What are some of the key takeaways you want our listeners to remember from this deep dive?
I think the biggest lesson is that there's always more than one way to solve a problem.
For sure.
You know? Starting with brute force really helped us understand that core logic.
Right.
And then refining our approach with stacks allowed us to handle those more complex scenarios.
Yeah.
And then finally, just thinking about the problem in a completely different way.
Right.
Led us to that super efficient single variable solution.
Exactly. It's not just about finding a solution. It's about understanding the trade-offs and choosing the best approach for the situation.
For sure.
And sometimes the simplest solution is the most powerful.
Absolutely.
Thanks for joining us on this incredible journey into the world of maximum nesting depth.
It was a pleasure.
Until next time on AI.Code.Cast, happy coding.